Recording in
Okay, everyone, let's get started here. Let me just put on my headset. So today we're talking about one of the last experiments. So today we'll talk about the Polyprotic post lab. So if you have any questions about the graphs, they should be very similar to what you did for the past two experiments. So save that spreadsheet so you have those equations already plugged in, and you can just duplicate it, copy data enter your data, and then regenerate the curve, first titration, and second titration graphs. So remember to turn those into the Google folder before this Friday. During the before the lab, because this Friday will be our last lab experiment. All right, so exciting news. Quite frankly, I wish you could have done more things other than titrations or buffers. We couldn't even do the buffers, but it would have been more exciting if you could have done some cooler chemistry with maybe some like metal complexes, seeing how they change color in solution. But I guess that will be for a experiment down the line in one of the other Chem 2 classes, I think 2C. You actually can do cool stuff with titrations, like titrating the amount of calcium in milk samples. So that was a pretty cool experiment I got to do when I was a student. You use something called a chelating agent, and you would use EDTA, or ethylene diamine tetraacetic acid, and that reagent is very good at coordinating 2+ metal cations, so you can remove magnesium and calcium from samples. And it turns out we did that on milk. So hopefully you could run some more fun experiments. So titrations are not all that bad. They're not all that tedious. Some are really cool to do. Okay. So we are going to talk about the post lab for the carbonic acid experiment titration. Okay, so let's just go through the calculations in the manual one by one. The graphs, they should be pretty self-explanatory at this point. If your graphs don't match what was in the manual for the first strong acid, strong base titration, you should probably redo it or reach out to me. For this experiment, you should probably see, and I'm guessing two peaks in two maxima peaks in the first derivative curve, and then two peaks or two places where the line crosses the origin for the second derivative. So those 2 points will be your equivalence points. So hopefully we can ballpark get an accurate value, and that's how you'll calculate do these calculations. Okay, so let me share a screen here. Hold on, okay, so we are going to go to notes again and type a new note here. Okay. All right. Okay, so we're going to, let me just zoom out here for a sec. Okay, so we're going to, so this is sodium, sodium carbonate titration with HCl. So we're doing this titration because we need to determine the amount of sodium carbonate in our solution, or in our sample. So we're titrating a known amount of sodium carbonate Not necessarily to figure out how much it is, but we're just doing it to calculate the Ka value. So to demonstrate that we can use titration to calculate Ka values. Okay, so for step one, we're going backwards, right? So the reactions we're doing is we have sodium carbonate plus HCl. Now that's going to be a reaction that gives us HCO3 minus plus sodium chloride. And here we would have to balance a few things here. So we should balance the sodium chloride too, and the HCl, which should be 2. And then we should balance the carbons here. You know what? I think what we should have done is, so you get HCl, 2HCl, right? Sodium carbonate plus 2HCl. And it looks like we have to balance. Oh, wait, they're not, it's not charged, right? Oh, okay. So hold on, let's go back here. So it's not charged. So one of them is going to be, so we do get sodium chloride, right? So let's write the ionic equation. So we get 2 sodium plus ions plus a CO3 2 minus ion plus H plus Cl minus. And you know, the carbonate and the acid will react to give us HCO3 minus plus 2 sodium, so we should put a 2 there, sodium plus plus Cl minus. So we should also put 2 there, and then that will give us 2H plus 2Cl minus. And so to balance this all out, we should put a 2 here, and then put a 2 in front of the carbonate. There we go. So 2 sodiums, 2 carbonates, 2 carbon. We have 2 bicarbonates, but that has 2 H's, so that gives us our 2 H's, and then 2 Cl minuses. And we see here the sodiums cancel out, and so do the chlorine ions. And our net equation is 2CO3 2 minus plus 2H plus gives us 2HCO3 minus. And if we look here, it looks like we could have simplified things. And so if we divide everything by 2, we get carbonate plus H plus gives us HCO3 minus. Now, I'm wondering why I couldn't see that in the balance equation. Maybe I'm just overthinking things here, but I wonder why. Let's see here. So 2 sodiums, 2 sodium chlorides, and 2. Yeah, it doesn't look balanced when you do it above there. So 2 sodiums. Interesting. Okay. So is it already balanced? Maybe I'm drawing a blank here. Okay, I think you need 2 sodiums here and 2 HCl's here. And then that will give you yeah, so it'll produce 2 sodium chlorides, so you need 2 HCl there, but it's still not balanced. That's interesting. Yeah, that's an interesting one. Okay. but we do have sodium carbonate. Interesting. So sodium carbonate is completely soluble. So I guess what you have to do is this is an interesting puzzle. I'm sorry it's taking this long, but let me see here. So 2 sodium carbonate plus 2 HCl. Hold on for a second here. Let's see what's going on. Okay. So in our equation, we have so we do have acid reacting with it. Okay. So our carbonate reacts with to give you bicarbonate. So I guess it just boils down to this. But I don't see why this reaction is not bouncing. So HCl, you're going to get 2 HCl's. So first you react with HCl to give you this reaction here. But then I think what's happening is the sodium carbonate, since there's 2 of them there, we have to include 2 sodium ions on both sides of the equation. So yeah, okay. So so if we erase this 2 here, that 2 there. Okay. It should still give us sodium carbonate should give us HCl3 minus plus sodium chloride. But the sodium chloride, I think we could omit it because they're spectator ions. So we times 2 here. We need to, so that's the balanced chemical reaction, right? The carbonate is reacting with the acid. So we can say that this is our equation right here. And if we wrote it like we did here, we say, I think we need to rewrite this. So let's erase this for now. Oops. Okay. So we need 2. I think we need 2 2 in front of here, and that will give us 4 Cl's, and then 4 of this plus. But then see, that's kind of strange. So sodium carbonate, that's sodium carbonate. So we have sodium carbonate. Sodium carbonate. So then we have this reaction. So it gives you this plus, I think it's 2 NaCl, right? Because for each sodium atom, we have 2 NaCl. That means we have 2 equivalents of this reacting to form bicarb. So I don't think it stops here. So I think the reason why we can't write it like this is because it'll further react to go to carbonate, or H2CO3. So the reaction we should be writing is this. Sorry about that. Is H2CO3 plus sodium chloride, 2 sodium chlorides. So here we have two sodiums, one carbonate, two chlorides, two hydrogens, two hydrogens. So that's the overall chemical reaction. So we can't just stop at bicarbonate because it doesn't like to stay there. But we have two reactions going on. We have this reaction forming bicarbonate, and then we have this reaction, HCO3 minus, getting another equivalent of acid to give us H2CO3. So this will be our so this one will be our K. So there's two reactions we have to look at. This reaction, so this is so this will be our first equivalence point. And here's our second equivalence point. Okay, so first titrations, we go to a first equivalence point. We're adding the second proton first, the second proton that gets lost. And then we're going to add the first proton in the second equivalence point. So this is our reaction here. Okay. All right. So the calculations we need to look at. So the first calculation is we need to find the pH at the second observed equivalence point. So you're going to use this value to determine the concentration of H plus. Okay. So the second equivalence point is where we determine the bicarbonate ion right here in the second equivalence point right here. So what we do is we find the pH. So the pH at this equivalence point. So this pH at second equivalence point. So say that pH is, I don't know, maybe 5.5. Let's see the pH. So let's say it's 5.5. So let's say it's 5.5, right? We're going to use our trusty calculation of the antilog to figure out the concentration there. So we get, so say pH is at the equivalence point. We're going to calculate H plus, and say our H plus at that point is now this is just a random number. Say it's 3.2. 1, 2, 3, 4, 5. Times 10 to -6 molar. Okay. So say this is about 5.50. That is an approximate value here. We'll calculate the pH. Okay. So first, what we're doing right now is calculating Ka1. So I'm going to list what we're doing here. So we're calculating. So let's erase this here. So this is the second equivalence point. We are calculating Ka1 from the second equivalence point. Now we're doing this because we know from the first expression. So the first expression is, let's just move this a bit. So the first expression for the dissociation of carbonic acid is H2CO3 plus water gives me H3O plus HCO3 minus. Okay, so this Ka1 expression, we'll leave it as 1, equals the products of H plus or H3O plus and carbonate ion over the initial concentration of H2CO3. Okay, so we're trying to find that point because at the second equivalence point, we have bicarbonate, and then at the second equivalent point, we're going to add enough acid to react with all the bicarbonate, and that will determine that pH value will give us the H plus. So that's our H plus value right here. Okay, now let's use the mass of So this is part one. So this is part A, B, or part one, sorry. Part one. Part two, now we're going to use the mass of sodium carbonate from our first trial. So we're going to, and the molar mass, so we're going to determine the moles of sodium carbonate. Moles of sodium carbonate. So we take our mass. So let's say, I use the mass of, let's see here. All right, let's say I weighed out 0.13. Let's say I have 0.1308 grams of sodium carbonate. Okay. We know the molar mass of sodium carbonate is 1 mole. Sodium carbonate, we can just add up all the values here. We should see a molar mass of, let's just calculate that right now. So sodium carbonate is 2 sodium atoms. That's about 22.99 times 2 plus 12.0. I'll just write it out. So the molar mass of sodium carbonate is roughly 2 times 22.99 plus 12.011 plus 3 times 15.999. Okay, so we add those all up. We get 15.999. Okay, 22.99 times 2 plus parentheses 15.999 times 3 parentheses plus 12.011. I get about 105.988 grams per mole. So we're going to put 105.988 grams sodium carbonate. And now we get a value of, so we're going to erase that actually. We get a value of, let's see here, 0.1308 divided by 105.988 grams. We get about 1.234 times 10 to the third. 1.234. That's an interesting number. Moles sodium carbonate. Okay, so we found our moles now. We found our moles. We found our acid concentration at the second equivalence point. So now we're going to use the moles of our carbonate species in the next step. So use our moles of carbonate species that we calculated above, and the volume of water we use to prepare our solution. We're going to determine the molarity of carbonate species in solution. Okay. So we don't know how exact. So we're doing this so we get exact numbers. All right. Okay. So our moles of carbonate. So what is our moles of carbonate in solution? So we measured out the first dissociation constant. Okay, let's see here. Okay. Oh, I see. Okay. Okay. All right. Let's just backtrack here. I just want to make sure I'm on the right page. Okay. Ah, I see. Oh, okay. All right. Yeah, these calculations are really complicated. So I think it's a good thing I kind of went over this because looking at this, I can see some headaches over here. Okay. So since this is a weak acid we're dealing with, we can say that the amount of carbonic acid in solution, given by this equation up here, that's going to tell you, or that's how we're going to figure out our Ka1. So we determine H plus, and if you go to the lab manual, it'll go through a series of calculations or rearrangements that I don't think you really need to worry about, like kind of remembering to reproduce. Um, what you should do is a takeaway is just follow along here. So, okay. So we know that the Ka1, it's reduced to the hydrogen ion concentration. If you look um, on page 68 of the manual, you'll see that we can reduce the equation to H plus squared over, and that's making some assumptions with the equilibrium expressions. So molarity here is the concentration of H2CO3. Okay, so by finding the concentration, okay, so they actually gave you a concentration here. It's very complicated if you don't read the fine print. So our molarity is A over volume plus the volume small v here. So this is big V and this is little v. I'll explain what they mean. So we calculated A. A equals the mass in grams of our sodium carbonate divided by the molar mass, which is 105.9. I just put 988. We can just do that, grams per mole. So we already determined A, and A is 1.234 times 10 to the negative third mole. Okay, so that's our A. The reason we do that is because that's the amount of carbonate that was originally present, and we know that the carbonate that was present, it turns into bicarbonate. So we assume all of it turns to bicarbonate, and then we assume that all of it turns to carbonic acid. And then since the equilibrium expressions for the second one is so small, we say there are weak dissociation constants, right? So we could make this assumption that our molarity, most of it is in the carbonic acid form, is because HCO3 minus, the concentration of HCO3 minus plus the concentration of carbonate ion is going to be very less than the actual molarity of the solution. And then that turns out that H2CO3 is going to be our molarity, because H2CO3 is a weak acid. And so not much of it dissociates to either bicarbonate or carbonate itself after we reach both equivalence points, is because they're both, the first step is a weak acid. So the second step is an even weaker acid. So we can assume that they contribute nothing to the molarity of M. So essentially M is, we're just going to assume it's all carbonic acid. Okay. All right. So we calculate A. What is V plus V? Okay. So V is the volume of solution. So volume of solution, volume of the original. Okay, so the original volume of solution that sodium 2CO3 was dissolved in initially. Okay, so that was probably 30 milliliters of water. Okay, so at the start we said we're going to dissolve in 30 mils of water, right? So yes, so there is some water. Okay, so it's 30 mils of water. Yes. Okay, and then V is the small v right here, is the volume of HCl added. Of HCl added to get the equivalence point. So V is the volume of HCl added to get to the second observed equivalence point. So that's what we did to get to the second equivalence point. Okay, in our titration. All right. Okay. All right. So if we have that equation, once we find Ka1, we can determine Ka2. Okay. So our equation now is, so say that's 30 mils, and it took me, I don't know, maybe like 19 mils to reach it. So say it took me 19 mils of the HCl to get me to the second equivalence point. Okay, so then our equation turns into molarity equals A over V plus V equals 1.234 times 10 to the negative 6. Sorry, not -6, but -3 moles divided by, so we need to find molarity, right? So this is moles of my sodium carbonate. So let's just write that a little bit neater. Moles sodium to carbonate, and we need to divide by liters to get our molarity in units of moles per liter. So we're going to say V is 0.030 plus 0.0190 liters. And that will give us a value here. Okay. So that will be a value of, let's calculate that right now. Okay, so we have 1.234 e to the third negative divided by parentheses 0.030 plus 0.019 parentheses equals, so we get 0. So let's keep so these volumes should have 4 sig figs. So let's keep 4 sig figs. 0.02, oops. 2518 molar. So our molarity now, our M value for sodium carbonate is this molarity here. Okay, so that's our molarity. Now we plug this into our equation here, Ka1 equals H plus squared over our molarity, and that will be our H plus molarity in part 1 is 3.2. We're going to have 3.2 times 10 to the negative 6. So let's not worry about parentheses here. I mean, the units here. And then our molarity, 0.02518. And we get a value of 3.2 e to the 6 negative. Okay. We're going to square it, divided by 0.02518. And we get a value of 4.0 times 10 to the 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the negative 10 as my Ka1. Okay, so that sounds way off. If we were to look at the Ka of carbonic acid, I'm pretty sure it's not that bad or that small. But, just take my values with a grain of salt and just calculate your value and put that into Hayden McNeil, and you should get the correct answer. Okay. So the reason why we can't, it actually doesn't list pK, surprisingly. pKa. Okay. Okay, interesting. So what's the Ka of carbonic acid? I know the value should be known. It should be known. Let me see here. Okay. So their value is 4.3 times 10 to the negative 7th. So not too bad. But my pH was off, right? So my pH probably was off because I was using different values. But see, the observed value is, so the actual for the first one, actual Ka equals 4.3 times 10 to the negative 7. So not too bad, but still more than almost 3 factors off. So that's the limit to my calculations here based on made up data. What I should have done is probably took one of yours guys' data and I actually used that, but I don't have there's actually no time, and I only there's no time for that, unfortunately. But hopefully your data will match up better with the actual value. Okay, so that's part 1. Just let me double check something real quick here. Use my textbook that I used to teach Gen Chem just to make sure the acid dissociation constants are very similar. Okay, let's see here. We have, so for weak acids, it's around 4.3 or 4.5 times 10 to the negative 7. So we're not too bad, not too shabby. Okay, so that's pretty good. So let's change this here, 4.5. Okay, so now that is the Ka. All right, so now let's go on to part 2 of the calculations. So make sure you generate those curves, get the equivalence point. So use that pH at the second equivalence point to determine the the pH, and that will give you the hydrogen ion concentration. And if there's any questions about the derivation of any of these equations we use for Ka1, please just read the beginning of the lab pages from 68 to page 67, 68, and you can do that, or just the beginning of the lab itself, 65 to 68. And you see there, oh, it sees Ka1 is already listed in our lab manual. So it says 4.4 times 10 to the negative 7. So maybe let's write that value instead. And it's pretty close though, but yeah, so they're just talking about 4.3, 4.4, 4.5. So we're going to actually determine this, okay, using these equations here. Don't worry about all these equations on page 67. What's important is the last part on page 68, where it tells you the equation for solving Ka1. So that's what you want to use. But how we got there is we rearranged. We know that both equilibrium expressions, they have similar terms that are in both expressions. So we kind of use that to rearrange and solve for Ka1. If you look at page 67, that's exactly what it does. It takes the Ka1 and Ka2, rearranges to rearrange the concentrate and solve for concentration of carbonic acid, and then concentration of bicarbonate ion. And then it used substitution for the carbonic acid expression to solve to have an expression with both Ka1 and Ka2, and you may see that on page 67. So then it does, since it takes the expression since H plus is equal to bicarbonate ion when it dissociates, you can then input that for bicarbonate squared, or I'm not exactly sure what they do in this next step. Let's take a look here. They take bicarbonate and then they solve for this expression here where it's okay, so I'm pretty sure. Okay, so since there's bicarbonate equals, or carbonate equals carbonic acid, so I think they, oh, I see what they did. So they inserted the expression from carbonic acid into the carbonic acid in this expression where they combined the two Ka expressions. So if we're looking at line 3, I'm sorry, on the lower half of page 67, they insert that some expression for H2CO3 cancel out the Ka1. Oh, sorry, no, let me see here. Oh, okay. So they what they did here, so they got the carbonic acid expression and got a expression that has Ka1 and Ka2 in the equation. So now they take the previous equation and solve for CO2 minus for the Ka2 expression, and what you get is HCO3 minus times Ka2 divided by H plus. And since we know H plus and HCO3 minus, they are equal for a given dissociation constant, that just equates to 1, and they just plugged in CO3 minus equals Ka2. So what that equates to is the previous expression, your Ka2s will cancel out, and your expression now is carbonic acid equals H plus squared over Ka1. So that's how they got those equations, okay? All right, but anyway, let's wrap this up and go to the second part of the equation, calculating Ka2. So for Ka1, you want to determine Ka1 for each trial, determine the average, calculate standard deviation and 90% confidence limit, and then upload those, upload that to, I believe, Hayden McNeil as part of the post lab. Okay. Okay. So yeah, I did tell you to follow equation 2 at the introduction, and that's what we did. So I'm glad we did that. Okay. I would have been more lost as you like you guys if I didn't do that. Okay. Now that we calculated the first ionization constant, we can determine the acid constant dissociation for the second less acidic proton. So we're going to calculate Ka2 from the first observed equivalence point. Okay, so we're going to calculate this Ka2 now. So now that we've determined all right, so first we need to find out the pH at the first observed equivalence point. So say my pH at first equivalence point, let's just say it's like, I don't know, 9.8. So let's say it's 9.81, okay? So that's our pH, 9.81. We can use this value to determine the H plus concentration. So H plus equals 10 to the negative 9.81. Okay, so let's do that. 9.81 here. 9.81, 9.81, negative 10. So we get 1.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I got 10 to the negative 10 molar. So not very big. All right, so that's part 1. 2. Following equation 1 in our introduction, we're going to determine the dissociation constant for the second proton, Ka2. Okay. So now that we know Ka, so we know that if we look at our expression here, we know that the H plus concentration is, okay, let's see here. Oh, okay. So when we combine the equilibrium constants, it gets to a point where it looks pretty scary. If you look on page 65 or 66, they're combining the equilibrium concentrations from two different things, because bicarbonate can act as an acid and a base, so they use both of them to determine the acid concentration, and using Kw as well. Okay. So it looks very complicated, but they simplify it that the concentration of carbonate ion will probably be much larger when it acts as a base, it will be much larger than the Ka1 because we're adding most of it to form carbonic acid. So that concentration will definitely be greater than the Ka1 because we add an acid to carbonate to form bicarbonate initially at the first equivalence point. So then we can ignore the unity expression in this equation. So you get rid of that unity term there, the +1 on page 66. And then what it turns out to be, you can ignore the Kw because the product of the carbonate and the Ka2 will probably be much greater than Kw because Kw is 10 to the -14. So we shouldn't have an expression that's that small. So then we can simplify this expression to say H3O plus. So I know that's a lot to take in, but honestly, what they're saying is just use this equation and just find the number. There's really no sense in trying to make any sense of it because it looks confusing. Okay. Because we know that the expressions here we have, we're adding carbonate to acid that forms bicarbonate. Then bicarbonate will add another acid to form carbonic acid. And then at that point, you have a point where the bicarbonate concentration can act either as a base or an acid. And then that will tell you that will affect the pH. So this big equation here, it's really telling you the concentration of H3O plus. So if you were to look at Ka2 and then Ka1, that tells you the concentration of H plus, and you can determine it by Ka2. So let's maybe write some of this out so it kind of makes sense. So Ka2 equals HCO3 minus over H plus times CO3 2 minus. Okay. So that is that expression. Now, if we solve for H plus, we will get H plus equals okay. We get H plus equals, oh, sorry, I'm looking the backwards direction. I should have done it the other way. Sorry. So Ka2 is when we have CO3 2 minus over H plus right, H plus, right. So it's Ka2 is HCO3 minus gave me sorry, I'm really out of it today. Sorry about that. Product here is H plus of Ka2 and CO3 2 minus equals HCO3 minus. Okay. So the solve for H plus would be equal to Ka2 times HCO3 minus. Okay, so that's how we get the first equation in this complicated expression here. Then on the bottom is CO3 2 minus, but they express it in a different way. So if you go to the Ka1, so Ka1 is equal to H plus HCO3 minus gives me H2CO3, so carbonic acid. Now, if you solve for H plus in this case, it'll be equal to Ka1 times H2CO3 over HCO3 minus. But so when they insert those terms, they actually, I think, when you're dividing it by this fraction, it flips. So so we know that so they kind of combine these equalities here. They yeah, they actually do something kind of weird. Because they take the equation now for the base, the carbonate base, and I think they also do this. They do H plus CO3 2 minus gives us HCO3 minus, and that expression is that's KB1 actually, or yeah, that's KB1. So that gives us HCO3 minus gives us H plus CO3 minus. Then when we solve for that, you get H plus equals K HCO3 minus over over CO3 minus 2 minus, sorry, times KB1, and then yeah, it ends up being right here actually. Okay, but so I think they solve for this because KB1 is actually equal to so KB1 is actually just equal to KW. KB1 is actually equal to just KW over KA2. Because the opposite of this is KA2, right? So it's KW over KA2. We substitute that there now. We get KW times KA2. And then overall, the expressions would, you can insert this for carbonate. And then yeah, so there's a series of expressions. Yeah, they relist it too, because then you can solve for H2CO3 in the terms of these other equations right here. So yeah, I don't understand really. Yeah, so there's a lot going on. They don't really do it step by step. So yeah, that's the problem here. So the first expression, you could think of it as like this expression here, and then they somehow divided it by 1 plus. I don't know where the 1 is coming from, honestly. And then they divided it by Ka1, and I think that's solving for H plus. Ka1 is right here. Where they flip it and the carbonate somehow gets included as a 1 here. But don't worry too much about how to derive it. You see, I tried to do it, but I don't think it's necessary. Okay, so let's just erase this. And now erase this. Okay, so the expression we want to use is H3O plus equals the square root of Ka1 times Ka2. All right. So now we use our equivalence point here. Okay, so H3O plus H3O plus so if we square this both sides, we get Ka1 times Ka2. So then our Ka2 will equal to our H3O plus concentration squared over our Ka1. So in this case, our concentration is at the first observed equivalence point. So that's when we form bicarbonate ion. So it's going to be our pH here will be 1.5 times 10 to the negative 10 molar. Okay. Squared. Let's just omit the units because we're going to end up having no units anyway. So it's not necessary, but it would kind of backtrack here. It does turn into molarity actually, but let's leave it unitless. Okay, then Ka1 we said at first was 4.0 times 10 to the negative 10. So that will give us our second Ka value, like so. So we take 1.5 e to the 10 minus, square it, divide by 4.0 e to the negative 10. And we get 5.6 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 10 to the negative 11 as our second Ka2. And if we look back in our lab manual here and look at the expression or the Ka value for the second equation, we get a value of 4.7. So actual Ka2 equals 4.7 times 10 to the negative 11. So not too bad here. Okay, so that's how you do those calculations. And then lastly, you would calculate Ka2 for each trial and determine the average Ka2, calculate standard deviation for Ka2, then calculate 9% confidence limit for Ka2, upload the Hayden McNeil, and then you'll be all done for this lab. Okay, so that is that experiment. Hopefully that even though it's ramblings, apologize for that. That is the experiment there. If there's any questions, please let me know, and I will answer them. Email. So if you email me, I'll definitely read them and get back to you before Friday. So if there's any questions, always let me know. But if there's nothing left, we're gonna call it a day there, and I'll see you next time.